stay in my office without talking to people face to face. So within the week, I test myself every day. So it's always 2 lines. This morning, the second line is almost disappeared, but still there. That means I still have virus in my body. So I decided not to go to the classroom and use this online meeting. Aria, are you going to record anything? Or do I need to record?
我说我有架摄影机。
Okay, you have camera. I will record my monitor as well. Okay, so today is actually the last lecture. Next week we will have our final presentation. So in this last lecture, I would like to talk about optimization with uncertainty. So let me first arrange a recording. I can do this. Okay. Okay, so what is optimization with uncertainty? Actually, I mentioned that a little bit last time. I would like to elaborate more this time. So there's a kind of design optimization problem that handles different kinds of things. So are you able to see the full screen? Aria? Can you see full screen?
Yes.
Okay, thank you. So this is just some stories, but focusing on this is just a design problem. This is what we had last time. A linear optimization problem where we are minimizing 2 variables A and B, and the dashed lines represent the descent direction of the objective function. When color becomes blue, it's lower. So going left and lower direction represent the optimal direction. And we do have 3 linear constraints. Each one was drawn in its representing color. And we have a allowable design space. So A must be larger than 5, B must be A and B both should be found within 5 and 150. It's not drawn from 5 to 150 because there is a triangular feasible space right here. So actually the variable bounds are not active. They are not useful. So only the 3 colorful constraints will be used. And if you have an initial guess like this, eventually you can use linear programming. This is the result, 24 and 96. Okay. However, here comes the uncertainty. If we can describe the uncertainty in distributions, and if they are normally distributed, then you can use this kind of shapes to represent its the area of higher percentage of the existence of the position. So what does that really mean? That means if you have a point 80 and 80, there's a really high chance the real design is not at 80 and 80. It could be somewhere nearby. So there is a tolerance. So say it again in real in regular human language. So let me use a real life example. If you are building building some product and you are looking for 80 for one dimension, 80 for the other dimension, and you produce 1,000 of it or 100 of it, and once you produce 100 pieces and you use rulers to measure both dimensions, you realize many of them are not exactly 80 and 80. They are 80 plus and minus some small number. And if you get all the measurement together and then study its distribution, it looks like a normal distribution. Most of them are reaching 80 and 80, but many of them could be smaller or larger. So in one dimensional, in 1D, it's normal distribution like this here. Let me use a pen. So it's like you're looking for some dimension at 80, but eventually you get a distribution like this. Okay, and also you are looking for dimension 80, but at the end you have a dimension. If you put this distribution and this distribution together near the center, it looks like a circle. It's a really poorly drawn circle. Okay, so that circle represents the area with the highest percentage. Okay, but you can draw this Gaussian distribution with different percentiles. You can say, okay, this area, this is 1 sigma, 2 sigma, or you can have a wider area, 2 sigma here. Oops, I don't want this. Hide this. What did I do? Okay, I have another sigma here. Okay, so if you have 2 sigmas from both sides, this is already probably 90%, really high percentage. So how do you know? You have to keep it. You have to get back to your knowledge about statistics here. So for each percentile, like this area, this is already 34% near the inside this entire Gaussian distribution. This is another 34. So 2 sigma, that's 68%. Another sigma here, another sigma, 4 sigma, that's already 95%. 6 sigma, that's 99.7%. Okay, so when we say 6 sigma, do we say both side or one side? It depends. Sometimes people call this 3 sigma design because of one side it's 3 sigma. Sigma means standard deviation. Sorry if you don't know. Some people directly call it 6 sigma. But however, the 6 sigma design often is used for representation from one edge. Here is a 6 sigma. Okay, so it's already 99 point many nines percent. So let me see how many nines. 4 nines, maybe. Oh, this one shows. If you are designing a 6, if you call one only the number of sigmas on one side, so then this is a 6 sigma design. Then the area underneath this Gaussian distribution with 6 sigma from one edge and 6 sigma from the other edge, you are having how many nines? 6 nines, exactly 6 nines, 99.9999998. This is very high percentage, almost like a 100%. Okay, so you are basically drawing the area of certain percentage. And what I'm doing here, actually I want to remove those. Okay, so what I'm doing here, I made two, they're actually circles. The A and B axes are drawn in different scale. Are they circles? Yeah. They should be circles, because from here this is one gap between two numbers. Here is 20, but 20 is like this big here. So in fact, if I draw this whole thing in scale, same scale, then this is actually a circle. So the smaller circle represent the 98% of existence of the design. A greater one, the larger one, is 99.87%. Okay, so if this is true, when we show if the standard deviation of A and B are always 2, sigma A and sigma B is always 2, then when you look at the optimal design, this was the optimal design, then there's a 50% of chances this red constraint fails, because there is a 50% of chances your design point is on the upper edge, right? So your failure rate for the G1 is 50%. Very poor design. Similarly, your failure rate for G3 is 50%. In total, I did count it, this whole area. It's around 90%. So there is a 90% of chance your design is going to fail one or two of the constraint, at least one of the constraint. So your successful rate is around maybe less than 10%, which is very bad, you know. So what we can do is try to find some new constraints. So those constraints were written in a specific way, so that they can be utilized for this specific purpose, optimization with uncertainty. We call them probabilistic constraints. So let me later on get iPad. Hold on. Let me hook up my iPad first. Okay. Now, this original constraint is called the feasible design. So when you have smaller than or equals to, this is a feasible design. But over here, I'm showing this in a larger than. So the probability of the larger than event should be very small. So this is the failure event. This is the save event, fail event. So the probability of failure has to be controlled within a very small number. And you can see maybe for specific reason the probability limit is different for each constraint. It's possible. Like you want a tighter tolerance or a looser tolerance. Okay. So over here, all these are so-called the failure probability. So the failure probability of all these three events should be within certain value, and they are small. Okay. So the reason why I chose 0.13 is because when I draw this circle, the bigger one is 99.87. Okay, so what's outside of this circle, it's exactly 0.13. Okay, good. So if you find the optimal solution within those so-called probabilistic constraint, you should be able to see this a smaller rectangle. And when you reach to this point, to this so-called probabilistic optimal solution, you will see the larger circle. It's actually tangent to the red constraint. So the area that is outside of the original constraint is controlled within 0.13%. And then the other one, this smaller circle is tangent to the blue constraint, the original blue one. So the smaller circle is 98%, which means whenever we calculate the percentage outside of this edge, outside of this red blue line, is 2%. Okay, so you precisely control the reliability. But how do you get those? Today I'm going to tell you more how you get those constraints. Okay? So this is the equation that you are dealing with. The probability of some failure must be smaller than some allowable probability. Okay? So how do you truly calculate probability? So it's like you are having integration and you are evaluating, this should be g function here. You are evaluating the function value of g within all the possibilities, and then you do a summation. Your basic integral is like summation. So but you only sum the ones with failure probability. So I can show you what to do. Let me turn off this. We can start to write a MATLAB code. So Aria, if my online lecture is having some issue, you need to let me know. Either message me or find a way to let me know. Otherwise, I have no idea what happened. Okay, so make sure I have my cell phone with me. Okay, great. We can start from scratch actually. Maybe I use my fminCon code because later on I can truly run fminCon. So that was maybe test 1, was it? Yes, this is my fminconc code. So I can save as a new file name. Okay. So let's say this is my fminconc code, and I can make a picture. I can run this code again, and I just wanna remind myself what the problem was. Okay, this was the problem. Okay. I think I turned off. Yeah, we don't want the linear constraint anymore. But I better turn on the constraints, the objective function and constraints, just to make sure I'm doing exactly that I expect. Okay, so I can show the points. Okay. Now, these are the this is the iteration procedure of um, of your the example from last time. Now let's start to add something interesting. So let's say the standard deviation of each variable equals to 0.1 and 0.2. How about that? Okay. So every time when my design moves, I will evaluate the failure rate. But I'm not doing something fancy. I'm just doing some counting. And whenever I evaluate the failure rate, I'm gonna plot them out. You don't need to worry. But I in order to evaluate, you need to sample the function. So you can be sure whether your design is fail or not. You need to make multiple samples. So for each time I sample, I'm gonna use 10 to the power of maybe 6 points, 1 million points to sample. Because like in real life, when how can you make how can you understand the failure rate of your production? You need to make a bunch of them. Otherwise, there's no meaning to mention statistics. Okay, so here we are sampling at each design point. So every time when we don't do we need, let me see. Okay, every time when we are here, that means MATLAB evaluates the function. So whenever it comes in here, I'm gonna I'm gonna compute the constraint values for the probability. Okay, so I should actually program over here. So this is for reliability analysis. Okay, so over here, whatever your x comes in, that's like the mean value. Okay, and I'm going to generate normally distributed points surrounding the design based on the standard deviation I mentioned here. So how do you do that? I'm using capital X1 as the random points. Okay, so in order to generate, it's a rand n represent normal. So random, if you say rand, that's a uniformly distributed. What's a uniform distribution? Uniform distribution looks like a box. Uniform distribution looks like a box. It's like you sample within a range, and the probability of everywhere is uniform. It's the same. That's why we call uniform distribution. Like this. This is uniformly distributed. This is normally distributed. Okay? So in real life, everything should be normally distributed, not uniformly. So if you say rand n, that's normal distribution random generator, and it generates random numbers from -1 to 1 actually. So what you can do is to create n of them, but you need to specify how the vector look like. So let me use 1 by n. So I will have a bunch of random points, and they are randomly generated and following normal distribution, and it's within -1 and 1. And I'm gonna multiply the standard deviation, first one, and I'm gonna plus x1. That's how you get randomly distributed points. If you need some notes, actually I'm in PowerPoint. I'm in Word, right? I can create a Word file. Just quickly type in some notes, so you know. So we call, let me use equation. No, this here. So we call design point inside the standard normal distribution space. Standard normal space equals to actually this. I will tell you what those means. I need a Greek symbol. Greek symbol, come on. My computer somehow is very slow right now. Maybe it's because I'm recording. Okay. Okay, those are the two equations that interchangeable. So x is the value in original space, design space, and u is so-called value in standard normal space, no standard normal design space. Mu is the mean of the normal distribution of your x. Sometimes we will use capital X. So capital X represent the random variable, and it's a distribution. It's random. It's not one value. But small x represent one value. So capital X could have 1,000 of them, and altogether we call them capital X. All these 1,000 of them. If I pick up one of it, that's small x. Okay. So and mu is the mean of all these 1,000 points. Okay. So you can say x is the random variable, and it's like a collection of all the x, and all the x behave like a normal distribution. Okay, and sigma basically is the standard deviation. Standard deviation of x. Okay, and they are, if it's a normal distribution, it follows this rule. Okay. So what I did was I randomly generate a bunch of values. What does this generate? This basically generates u. Okay, and then I use u to multiply my sigma, and then plus the mean value. So basically, this is exactly so-called the u times sigma plus mean. Basically, mu. Exactly this. So then I will get all the randomly generated positions of x. I do the same for x2. Generate same amount of points. Don't use the exact same random generate points, because what you have in x won't be the same in y. You should generate them separately. Okay, and the second standard deviation, second variable. Now we want to plot them out in our figure. So what you can do is to plot all the capital X1 and all the capital X2, and this time we use some tiny red points, red dots, marker size I think 6. No, maybe 10. Try that. Just pause right here. And then one step. Did you see all these? Okay. Too large. Marker size maybe 3. Okay, try again. Yeah. I want them to be transparent. So it's just a color. So red is 1, 0, and 0. and maybe 0.2. Does it work? Does it work like that? Let me see. No, it doesn't. Let me see. I want to adjust the color so I don't block the point behind it. Come on. It's running very slow right now. Okay. Color. Okay, I should say alpha. There's no alpha? Really? Marker size. Legend. I cannot make transparent points? Really? Marker face color? No. Let me see. Alpha points. Can I transparent? Okay, no. It doesn't. MATLAB doesn't generate transparent dots. So if I always make this drawing, it will block where I draw them. So maybe let me prove it to you that this is the area representing normal distribution. We can try to make one ellipse. Let me how to draw one ellipse. So the function for ellipse should be should I use symbolic, or maybe I use a easier? No, I shouldn't, because I need to make counts. So I'm drawing. Basically what I'm planning to do right now is to draw one ellipse and then make counts of the dots and show you how many dots are inside, how many dots are outside, and then truly count the what that ellipse represent. So if I'm looking for a elliptic area that keeps 90% of our points in there, so that ellipse should be having certain size, so it will become a container of 90% of those points. But I need to draw this ellipse precisely, right? So I can actually draw a circle inside standard normal space and then convert it back. Yes, that's actually easier. It doesn't sound easy for you, but it's easier for me. So let's say I'm going to draw how about 1 sigma ellipse. Okay, so in order to do that, I'm actually transferring back to the standard normal space, draw a circle with 1 sigma, and then convert it back. Okay, so that means I need a variable called theta, and then the angle ranges from 0 every time I increase by pi over how many points? Maybe I use 20 points to draw a circle. 20 points. Okay. No, maybe not enough. I need to draw a nicely drawn circle, maybe 50 points. Okay. So I have a theta until I have pi. Okay, good. And radius in the standard normal space is gonna be 1, so I'm drawing 1 sigma. So then the coordinates on the parameter would be basically a bunch of I call them the U points. U points would be radius times sine theta. Yes, that's fine. And then this is horizontally horizontal vector theta. This is a horizontal vector. So should I make it a vertical one? Let me think about it. It's okay. Let's make it horizontal. So the other row, I make it cosine. So this will be a bunch of points inside the standard normal space. I just need to convert them back to the normal regular space, X space. The way we convert it is to follow the equation here. I have a bunch of u's. Now I just need to say this times the but when you multiply, it's an issue, because right now this is a bunch of. I can show you if I make a pause and show you what I have right here. Okay, I basically have 51 points from 0 to pi, right? Actually make a circle, I need 2 pi. 2 pi here. So maybe 100 points? No, 50 is fine. Yeah, that's at the end. This gives me 101 points, right? 101 points. Basically, if I execute this line, one step, I will have a bunch of, like the first one is 0 and 1. Sine. Cosine first. Sorry, cosine. It should be 1, 0. Cosine and sine. Sorry. And then actually I can draw this in a different space to show you. So maybe I make a figure 2. So figure 2 would be my standard normal space. Okay? And then I will say plot. They are I should say U 1 comma everything, 2 comma everything, and a bunch of blue dots, marker size 10. This is fine. And then axes equal. Let's pause right there. So this is what I made. Basically a bunch of points, like a circle, and it's representing the area within 1 sigma. 1 sigma inside the X space, and also 1 sigma within the second variable. 1 sigma within x, 1 sigma within y. But it's in the standard normal space. So the mean value is 0, 0. And the width is basically 1 sigma. This is 1. This is also 1. And I'm converting all these to here surrounding my design point. Okay, so now I need to do some multiplying. When I do multiply, I need so u is 2 by 101 points, 101 vector, and my standard deviation is 1 by 2. 1 by 2. So if I direct multiplying them, I get 1 by 101. Yes. So STD times U, that gives me 1 by 101. So 1 by 101. But I don't want 1 by 101. Let me write it down. My sigma now is sigma 1 and sigma 2, right? And my coordinates, u coordinates, basically it's like u1 of the u11, u21, u31, u101 and 1, right? And then second line I have all these, but the second coordinate, no, second coordinate. Okay, here I just generated my data in this way. So what I want to do is this value multiplying sigma 1. So all these row multiplying sigma 1. And all these, and the entire row here multiplying sigma 2. So what I can do is maybe I need to stop being lazy so you can understand what I'm doing. So basically the entire row of u, I'm gonna multiply basically standard deviation 1. Yeah, basically I'm doing this, and then I need to add the mean value. Mean value is my x1, so that gives me a bunch of points. So there are x points, but there are the x points of the ellipse, x1 of ellipse. Okay. Do the same thing for x2. Now get back to the figure 1, and now we are going to draw exact same thing again, but this time a bunch of x1 and x2. Okay, and let's pause here. You see? Let's take a look. Basically, this is the area represent 1 sigma. Okay? I can do the same thing for 2 sigma and 3 sigma. So let me break it. I can do exact same thing, but I just need to repeat the whole process by enlarging the radius. So I can actually and 2 sigma, 3 sigma. Okay, let's just take a look how it looked like. So I just copy the whole thing, but this time radius become 2. I don't need this theta again. I recreate u. I don't need to draw in figure 2 anymore. And I create all these same calculation again. I'm already in figure 1 and plot again. Okay, so radius 3, just stupid way, just I didn't use a for loop. So let's see, running the code. Okay, one step forward. It's kind of interesting, right? So what does 3 sigma have? 3 sigma is actually already 99.87 99 something percent. Let's remind ourselves. Normal distribution. Here, 3 sigma is 99.73. So supposedly there are a bunch of points outside of this 3 sigma ellipse. So can we count? Can we truly count? Yes, we can. Let's try it. So in order to that's okay. Let's keep the whole thing. So let's count how many points outside of 3 sigma ellipse. Okay, so how do we do that? I randomly generate all these 1 million points at this step. Then I'm gonna convert them to the standard normal space and see if it's outside the circle with radius of 3. If yes, it's outside. If not, it's inside. That's a much easier way to evaluate, right? If I always convert back, if I want to do reliability analysis, I convert back to the standard normal space, because inside the standard normal space, everything is circular. But if I'm in the original space, it's in an ellipse shape. Okay, so now so how do I convert all these to the standard to the standard normal space? I have a bunch of x1. X1 is symbolic. Why? Oh no. It's not symbolic. It's a horizontal vector. Okay, good. So converting, I'm gonna use this, the first equation. So if I all these 1 million points dividing the mean as not minus the mean divided by the standard deviation STD1. Actually, this is it. So I'm going to call this capital U haven't been used. Capital U1. Okay, good. So I'm going to do the same for capital U2. Okay, so now this converts everything to standard normal space. Do you want to see a proof? So go to figure 2 and then plot them. Plot basically this. But in figure 2, I need to say hold on. so I can plot something new. U1 and U2. Oh, this is wrong. Okay, let me change the color. Blue points. And here, yeah, that should be fine. This one I make it larger. This one I make it smaller. And I'm gonna pause right here. Oops. you cannot see the original stuff. So with way too many points. So there. What is the command to plot underneath? How to plot behind all objects in MATLAB. Behind. Front and back. Okay. Render. Children? Really? No, it's too complex. Is there a property to represent parent child? Really? Is there a way to swap its order? Visible because my blue points is always plotting in front of the red points, so I don't see the red points anymore. Really? Child? No. There's no ordering. Oh, because I made them blue. I made both blue? Did I? Yes. I made them both blue. Then you won't be able to see it. If I make this one red and smaller dots, should be fine. No. No, cannot see it. Just want to find a way to move something to the back. Okay, obviously I couldn't find it. Stacking order, okay. Truly, is this a trial thing? Really? Okay, then it's some other time. I need to learn it later on. Okay. Because there are way too many points. Or we can just for now, let's just make a 100 points. Then you can see it. If we don't make that many random points, you should be able to see it. See. These 100 points Some are inside, some are outside. Okay, but 100 is not enough for statistics. Okay, now we need to do counting. So there are imagine a million points distributing surrounding this circle, many of them inside, many of them outside. And this circle was 1 sigma. I'm actually trying to evaluate inside or outside 3 sigma. So the easiest way to evaluate it is to check what's the radius of it. What's the radius of a specific point? Like, for example, this particular point. What's the radius in this standard normal space? So it's very easy. I'm gonna say radius u. So it's going to be u1 square plus u2 square, and then take a square root. But they are vectors, so I need to use dot power. Okay, so I will have 1 million radius. Now I need to count how many of them are larger than 3. So radius larger than 3, this gives me a bunch of 0 and 1s. Then I just need to sum them up divided by the number, a million. So at the end, this is percentage. Percentage I can multiply 100. So this is the failure. It's like a failure rate, or I would say 3 outside 3 sigma. Okay, so let's stop here. Run it again. Okay, so compute that outside 3 sigma. 1.12. Was it accurate? So 3 sigma was 99. It's not very clear, this one. We'll find a better one. This one. Okay. Okay. 3 sigma, it didn't say, no. Oh, 99.73. So when we count what's outside of 3 sigma, it was 1. How about we count what's inside? That's easier. Let's count what's inside. So change to smaller than and equals to. Equals to is important. Maybe there's one exactly 3. Okay, so I'm going to rename this inside. Okay, and I'm gonna just display on the screen. But I feel like we need more in order to show a more precise accuracy. 10 to the power of 10 points. Okay, let's run it. Oops. Too many. 74.5 giga. That's why my computer is running so small. What did I do? Did it change it back? Oh, here. It's too large. Maybe just 8. Oh no, I didn't. Did I break it? Did I break it? I did. Okay, too much time. Don't do it. Don't do it. It's too many points. Maybe just 10 to the power of 7. I think these are just way too many. Don't do it. Don't do it. Stop. Stop MATLAB. Okay. I'm going to ask MATLAB to go to sleep. I guess it eats out a bunch of memories. Yeah, 4 gigabytes of memories. Force quit. This I use too many there's too many standpoint points. That's way too many. So optimizations where here. Let's open the file again. So now you can tell if you want to do statistics in optimization, it's taking a lot of time. Because every time you need to evaluate like a percentage, how do you evaluate? You basically count, right? I guess we just get back to 10 to the power of 6. That's fine. We may not have enough accuracy. But hold on. Okay. It is not responding. Okay. Now, good. Just 10 to the power of 6. Pause right here. Run the code. So if in real life, at every design point, you are evaluating how good your current design is, you need to make 1,000,000 of it, and you need to check whether each design is good or bad. It's like 1,000,000 check. So it's a really challenging task. Okay, I made one step forward. Okay, 98.88. Is it accurate? No, it's not. It not because supposedly if it's for 3 sigma should be 99.73. So it's close, but not very precise. And reasoning, let me see. Maybe we need even more points, or the random generator may not be very precise. Okay. Anyway, that shows what you see right here. Actually, there are 99% of points inside, only 1% of points outside. And you even it's 1%. It feels like there's many points, because there are 1,000,000 points right here. So 1% of points, 1% of 1,000,000 points outside of the largest circle right here is looking like this. Okay, now let's get back to what we want to do. But this time I'm not going to make I'm not drawing the dots anymore, because if I draw the dots everywhere, you will see a bunch of dots. So instead of the dots, I will be drawing the ellipse. Okay, every time when I move to a design, I will draw the ellipse. Okay, and let me just draw the 3 sigma ellipse. So I need to keep this. No, I don't need this anymore. I don't. Yes, I do. Later on, I'm gonna check how reliable my design is. I'm gonna count. Okay, so but I'm drawing the ellipse. So forget about the 1 sigma stuff. Whatever is 1 sigma. So let me just change this one to 3. So this is 3 sigma. And but I'm not plotting the. Oh, this is okay in the U space. This is plotting. I don't even need U space anymore. I'm turning this off. I do need this in figure 1, yes. Okay, and I don't need these two. So this is giving me the blue circle, blue ellipse with 3 sigma. And then do I need to count this anymore? No, I don't. So I will get rid of this part. I'm not deleting them. I will share this to you so later on you can learn from it. So I should be making those ellipses surrounding the design point every time when MATLAB call this function. Yep. This time I'm making it a curve, a truly ellipse. I don't need marker size, but I need line width. I just this. I should be able to see a bunch of ellipse. No, this is not what I want. I don't want to see the points. Come on. I don't want to see the points. Ah, here. I don't need to see the points. Okay, run it again. So it's like this. Yep. So you will just see. Yep. Exactly what I want. Okay, so you realize when a design point move, the ellipse represents its 99% existence surrounding the design point. Okay, so now at the actually everywhere, every time we reach to a design, what's the failure rate? You basically just count how many points that is violating the constraint. You just basically count. Okay, that means you are plugging in this function a million times. Okay, because you have 1 million points. So I'm not going to do that everywhere because that's gonna take a long while. I'm going to just evaluating at the optimal solution. Remember, we have this is your optimal, right? So we are going to check the the failure rate at optimal. Okay. So how do we do it? We basically plug in. I need a random generator again. Here. Okay, but this time you're using this point. This is your optimal. First one and the second one. Okay, so basically these are 1 million points at the optimal. Okay, and then you are going to plug in these. Instead of plugging in, I'm just doing it outside. Because if you call this function a million times, that's a long time. We don't want to do that. Just ask MATLAB to calculate for us. Let's just do it outside. Okay, so this is my G1 and my G2, right? So you're going to evaluate those in a certain way. So over here you just replace it by this x1s and x2, x1 and x2. So dot power dot multiply. Okay, and then you basically have 1 million function values, and you are going to check whether it's positive. Positive is bad. Positive. So you sum them up, divided by the number of points, multiply 100, sum them up, divided by n, multiply 100. That's your failure rate. So fail 1, fail 2. Okay, just show it on the screen. Done. The failure rate for G1, basically G1 is the red one, is 0. So every point is on the safe side of red constraint. So it will never fail. But for G2, 50% of the points is outside of this green curve. So overall, your design have 50% of failure rate. So let's try to change our objective function. And let's try to hit this corner. Okay, let's try to hit this corner to see failure on both constraints, just to see it. Okay, so if I want to do that, I need to change my objective function in a certain way. My objective function needs to be, so change this one. So if I say plus 3, and then x2 probably minus 6. How about that? That should do the magic. Okay, so I need to change this function over here. A new function. Just for the purpose of what I said. Okay, run the code again. See? Interesting. So at the end, you realize optimal is right here. It's not at the corner, because of how my the function was generated. Okay, if you want to see, the object function is like an ellipse. So actually, the decent vector actually goes like this way. Goes this way. So it's having a tangent right here. It's even better. So it's even better for my example, because if you observe the last ellipse, around 50% of points is outside of the green boundary, and a fewer percent of points is outside of the red, maybe 30%. So let's check the failure rate. Failure rate for the first one is actually 9. It looks like 30%, but it's actually only 9%. because most of the design points accumulate at the center. So what's above the red curve, only 9%. But since this ellipse stays on the green line, whatever on the left, it's close to 50%. Okay, so that's a failure rate, very bad. So the only way to make a good design is to have tangents of the red and the green, and if you can find a point right here, then you can precisely control your of your design points. So get back to my PowerPoint. But now you realize whenever you compute this failure rate, it's very time consuming. We solve for optimal, and then we only evaluate reliability at the optimal. But what do you do next? Because what you truly want to do is to do this control. The probability, your new function is a probability. So if I truly ask MATLAB to, if I write this exact formulation inside fmin_conc, what's gonna happen? Actually, let's try it, because that's easier to program, but it could take a longer while for MATLAB to compute. So that means whenever we are here, we are not truly formulating this. We are evaluating the probability. So I'm gonna convert this into a true probabilistic constraint. So if I want to do that, I will need these two. I need all these. So this randomly generates design points, and then I'm truly computing basically this. Let me see. I already have random x. I just plug in, yeah, just like that. This is basically it. Yes. This is failure rate of G1, failure rate of G2. Yes. But here, yeah, this is failure rate. And we want, for example, so this was no longer my constraint. Constraint would be C1 could be failure rate must be smaller than, so minus, if I control this to 99 point, how about 90%? 90%. So smaller than 10. Smaller than 10. But if I do it, then you won't be able to see the tangent. So this circle 3 sigma, I better follow this 0.13, because 3 sigma circle tangent to a line gives 0.13% of probability on failure side. Yeah, I know, 0.13%. So this is like your failure rate must be smaller than 0.13%. And then C2 fail 2 minus 0.13. So this is basically programming exactly what this means. But every time when you come in, you have to randomly generate points again, because every time x is different. You need to regenerate a million points and then re-evaluate what's the current failure rate for that particular design, and then returns function values. Okay, that's interesting. If I do that, I think we can still plot the ellipse. That's fine. We don't. Yeah, that's fine. We compute the failure rate at the optimal. Yeah, that's interesting. Let's see how it goes. Okay. It does something, but not very well. Why? C1 and C2 fail one, fail two, right? So I must have given MATLAB a really. Did MATLAB truly do finite difference over there? Oh, it did. Trying to converge. Yeah, it truly did finite difference. So maybe the probability changed too little or too random. Because from our previous experience, whenever we perform probability analysis, it's every evaluation is different. So because it relies on random generator. Okay, let's make our life easier. Let's try not to use 0.13%. Let's try to solve for a 1 sigma problem. 1 sigma. This is let me count. What's the percentile? Normal distribution. Okay, here. So this is 34%. This is 50%. So together, one side is 84%. So at the tail, this is 16%. So let's try that. 1 sigma, one side is 16%. So if we want to control, I want to control the failure rate within 16%. So just 1 sigma, 16%. Now, I think this will make everything easier. But in my other codes, I need to only show 1 sigma. Only show 1 sigma. Yes. Okay, everything's right here. This is yeah. Try this. No, it doesn't work. I don't know why. Okay. I guess that's why my PhD work was important. Okay, well, I tried to program it, but it didn't work. So in my PhD years, we realized we cannot just use this. So we decided to follow something called the Hasselhoff and Lind reliability index. So what is that? That requires some hand drawings. Okay, hold on. Let me see if I can share what I have on my iPad to you guys. Let me get back to sharing here. Change monitor. It doesn't. Share my iPad. Let me try again. Well, it doesn't allow me to share my iPad. If that's the case, I have other tricks. Hold on. I have other tricks. Let me. Ah! My iPad can log into the Meet as well. Hold on. And my iPad could be sharing. Hold on. Okay. Uh, Let me turn off screen here. Try to share. Continue. Share. Yes. And then change to app. Horizontal. Yes. Okay. Now what happened was originally you have a G function. This is like a very original design. This is a save design, right? But now small x become a capital X. This is actually a random variable now. So we now need to evaluate the probability. So this is the fail event. This is called the failure probability. And we believe this probability is normally distributed. So this is a whatever event, right? This could be treated like actually I'm repeating what I wrote. This is assumed to be normally distributed. So if this event is normally distributed, then you can write down something like this. I better convert it back to standard normal space. So we need to convert to standard normal space. So since we have u equals to x minus mu over sigma, okay, so it's like for the entire distribution, the capital X follows this equation. So the difference between here and here is that this is a distribution, entire distribution. So that means sorry, that means the capital U is also a distribution, but inside the standard normal space. Okay, so if I do that, I can basically after conversion, it's like everything is in the standard normal space. Okay, so we discuss everything in the standard normal space, and uh, let me find a better way to explain this. Oh, maybe we need to do something before that. We are going to do Taylor expansion. First, sorry, Taylor expansion. So if we do that, g function at the current design point, for example, so-called x0, minus x plus, and this is gradient. Okay, this is just linear Taylor expansion. And then the variable is right here. The rest are just numbers, a bunch of numbers. Now convert to not yet convert to, since everything is distributed, so I should make it a capital one, right? Just like here, everything is distributed. So now I convert to the standard normal space. When I do that, I basically use the equation on the left. Okay, so basically at the end I will have some g. I'm gonna use g0 for short, and then actually this guy is mu, right? Because that's where our mean value is. So at the end, this whole thing is capital U times sigma, right? And I'm gonna call this just a number, gradient g0, okay, larger than this. So we can kind of rewrite so we're just in the standard normal space, we're checking whether your u is larger than some value, okay, and you want this to be smaller than something, but we didn't talk about something yet. Right here, if we revisit our original constraint, we actually need a number. For example, based on what we said, 34, 84, 16%. So this is like a 1 sigma design. You allow 16% of failure rate. Okay, so if you do that, at the end, you are, after everything, you end up with something like this. And on the right hand side, this is still a number, but in a percentage in the standard normal space, it's like a distance, okay? Because in the standard normal space, this is For example, like I said, this is like U1 and U2. It's like we are talking about a circle with radius of sigma, and we are studying some points outside, and it's like you are making a cut. It's like you're cutting a line, and then you wish whatever that's over here on one edge is 16%. So it's like you're studying the coordinate. Actually, you're studying the coordinate, like this point. It's like you're trying to figure out what's this, and it's actually this is one. Okay, so it's like you wish your design u must be greater than something like -1 in this particular drawing. If your design u1 is greater than -1, you're on the right hand side. You're safe. So the benefit of having everything inside the standard normal space is that you're controlling distance, and you are thinking in this standard normal scale. Okay, so uh, what's happening on the right hand side? Actually, you need to compute so-called the actually this is this. But what is this? This is so-called cumulative CDF. CDF. Cumulative distribution function. So if I go to MATLAB and say norm CDF -1, see, 16%. So that's, oh, you don't see it. You don't see it. You are in my iPad. You are in my iPad. So let me. You are in iPad. How do I? I should share as well. Share now. Okay. If you say here norm CDF -1, it's 16%. Exactly what I draw on iPad. So what's going on? But what is a norm CDF? Norm CDF. Is there a definition? No, it doesn't show. Here. Norm CDF. But this is CDF. I need here. This is norm CDF. Calculating the accumulated distribution from negative infinity to some point, to somewhere inside the normal space, standard normal space. So let me write down something on iPad. Okay, just like what the web page showed. Norm CDF with some value. So in MATLAB it's called a norm CDF. This is like in MATLAB. What is it? It's like a accumulation of distribution to certain point. Over here we use a small f, function of u du, I think. So this is a standard normal space. So standard normal distribution. So this should be 0. Here is 1 sigma, here is 1 sigma, and here is negative infinity. And at particular position u, if you compute the area from negative distribution, negative infinity to certain point u, the area equals to this, so-called CDF function. Basically accumulated probability. So why do we do that? Because we are calculating one side of the function, and we want to evaluate that and then keep it within 16%. So if you want to keep it within 16%, it's like you are controlling this and making sure you, in the standard normal space, you are 1 u away from it, 1 sigma away from it, but only in the standard normal space. Okay? So at the end, you are doing something like this. And what in my PhD work, I was doing this. You can actually even convert this whole thing into a new way. You need to, otherwise it cannot be utilized easily. So you need to rewrite in this way. You want to say let me see. You basically have to you have to convert the left hand side to a function so-called negative beta. Yeah, you need to do this. Okay, but what is beta? Beta is so-called the reliability index. Okay, and it's like -1 is what you are looking for, the gap between your in this particular drawing. So here is -1. You want to keep this is where your design at 0. You want to keep 1 sigma away from the constraint, but u is where your constraint is actually. So now you need to move your design point so your u is not right now your u is greater, having a larger distance away from -1. That means your failure actually in this particular case is good, because the desired goal was to have a design in the U space, and here is -1, right? You want to keep your design away from the constraints, so over here it's 16%. 16? Yeah, 16%. Yes. So if after the conversion, maybe at the end you have a new design on the left hand side. The left hand side, right hand side is fixed because the desire is 16%. For your current design, maybe at the end you found your U is here. So this is the desired. I should say the worst failure rate acceptable. Or I should say the allowable failure rate, right? We only allow this. But if in some particular design you realize your failure rate is this big, so maybe this is already 40% in some particular current design, then this is violating. So we need to move the design point until when you move the design maybe toward this direction, then that means this boundary moved toward left, and you wish to move your design further until you are right at the exact distance away from the constraint where there's a 1 sigma distance. Okay, so that was the idea. And there's a lot of work to explain, but I just want you to know that's how you can do optimization with uncertainty. Now get back to my PowerPoint. I need to stop here. Stop the sharing. Okay, and then share right here. So it turns out we have to study so-called beta. So this was the derivation that I mentioned. Don't worry about the so-called MPP. It's too much work. So anyway, at the end, this is the reliability index. So basically, the current distance away from the constraint for your design, and this is the desired distance. So for me, for the earlier example, this is like 1. Okay, and this is a current design. So it's like a current you need to keep a distance. At the end, you have larger than, right? Beta larger than 1. So it's like you keep a distance of 1 sigma away from the constraint. Exactly like that. So if you formulate in this way, you don't even need to perform the random generation. You just need to figure out how to do this. But it took me several years to figure out in my PhD. But at the end, I will tell you how it looked like. There were some issues in a very traditional method, but here, you need to do this. Let's try this in MATLAB. I hope I still have enough time to program this and make it work. Okay, so but I need MPP. Then it's a lot of work. Then maybe not. Maybe I will just turn on my old code. And like I said earlier, there was some mistake in my old code, but maybe I can fix my old code. It's easier. So my BDO in this field is called reliability based BDO. reliability-based design optimization. No. Where did I put it? Let me see. Maybe on the desktop. Secret. Here, RBD. No. RBDO. Okay. Try this one. Try this one. Plotting. Nonlinear math. Go. Really? Did it work? No. Oh, that is too much work. Never mind. Forget about what I said. Never mind. Maybe just here, just see this. Too much work. Okay. So yeah, basically by solving those, you can get what over here. Okay, and yep, different starting points. The method can find the solution. Okay, this is the nonlinear problem. Okay, and I enjoy solving this problem where you can see where this circle is having perfect tangent with these two curves by the allocation of those two probabilistic constraints. So how come the probabilistic constraints are linear and the nonlinear constraints are the original constraints are linear? Because whatever that was done in reliability was based on a linear approach. Like I show you in the iPad, I use linear Taylor expansion. So for probabilistic for the reliability analysis, it was linearly approximated. So we often call this linear first order reliability method. First order FO reliability method RM. So FORM form. We often call these form, and they are so-called the SORM, second order reliability method. I mainly focus on forms, and there are some other researchers work on SORM, second order ones. Okay. Yep. Let me show you some other works. So that was 2009. How many years ago? 14 years ago. Wow. When I was a PhD student. 2009, I was 27 years old. 27 years old. What? Okay. I hope this PPT works. There are more RBDO in here. This one. This was the first PowerPoint that I made this. This was the first time that I made this, and I still use it. So this explains RBDO in a nicer way. Usually, this is your deterministic optimal design. If there's uncertainty surrounding your design point, you can draw a circle to represent its 99% of percentage near the optimal point. But at the end, at your optimal point, you have 50% of failure rate. If you can find some kind of a probabilistic constraint inside the feasible space, you probably can find a better point where the red circle is tangent to the original constraint, so that you can control your failure rate to within certain percentage. This sums up exactly what I mentioned in the past 2 hours. Okay. Does it work? No. Let me see. So this explains the whole thing in a 3-dimensional way. Yeah, this is the final equation. In the past, I like to do this animation. Now I don't. Too much work. Too much work. And it screws up when you change Mac to PC. Okay. Yeah. Similar approach. Okay. Does it play? No. Where's the file? Let me see. It was too long time ago. Okay. Let me see if I can find cool stuff. There was a paper about. Let me see. IDTC. This one. This probably is the most recent RBDO paper I published. After 2016, I became so busy, so my research on this topic stopped. I'm still waiting for someone to work on this. And from here you can tell it's very intense in math. So I published this a long time ago. I call this I invented 2 methods. One is called Iogra, the other one is Actra. Same PPT, but in the previous works we realized whenever a distribution is not normally distributed, it's very, very difficult to solve. So, because in the original plan was to convert everything into the standard normal space and then try to figure out the shortest distance between your design and the constraint. That's basically the concept of most of the reliability-based design optimization problems. And there are some other approaches. However, what if your design is irregularly distributed? Then you cannot convert to standard normal space, but because you have no idea how to transform it. Okay, so I published this paper. I think this is the paper that helped me promote to full professor. Maybe this one or the other one. Anyway, yeah, we realize any random distribution could be approximated by a summation of a bunch of smaller Gaussian distributions. So like a smaller red dash Gaussians. Okay, this, don't be scared of this. This is basically the general equation of a Gaussian distribution. I basically sum them up. I made n of them, and this is so-called the kernel density estimation. So if you have arbitrarily distributed constraint, you can approximate the distribution by this kernel density estimation. Okay, and then what I did was to formulate those using math. So at the end, I modify what I did earlier. This is again reliability index, and I basically at the end it's a summation of all the small kernels, and you basically took a summation of it. And over here is a cool approach by this cartoon. Basically, this is the mean of your design. Now your distribution looks weird. You basically make smaller Gaussians, basically smaller circles, and the sum of them is the shape of your original distribution. So it's like you are performing reliability analysis one by one. You're performing reliability analysis one by one, and then put everything together. That's basically what I did. That was the first paper. Yeah, that's it. The second paper, a different approach. So again, I basically have a bunch of like a kernel points, and then find a straight line, and then just project every point on the straight line. And then for each point, it represents a distribution on the straight line, and you find the overall failure rate. So the goal was to move the point along the line and trying to find the position where you can control the exact failure rate. So at the end, it's like this. You move exactly to here, so you control your failure rate. The purple area is like the failure rate. You want the failure rate to be exactly what you're looking for. Okay, and a bunch of math. So there's a comparison between two methods. I made comments about the differences, and some crazy approaches, some crazy codes. So you can make distributions in very weird shapes, like a heart. And for traditional methods, this heart shape distribution can never be solved. So I even made a shape like a Facebook like. So I call the like distribution, and I made this a weird star. This is like a corona. Oh, those are traditional ones. This is normal, uniform, and this is log normal distribution. This is log normal but flipped in a weird way. Something called Weibo distribution, a flip Weibo, Gumball, another distribution, and a flipped Gumball. Okay, and I try a bunch of things, and then they all work. That reminds me, maybe I have a good code somewhere. Let me see. No. Video. If I can find something called Gram. Come on. My computer. It's not working with me. Come on. Not working with me. Okay. Do I have a code here? Oh, here. I hope this one works. Try it. Oh, okay. Well, what happened? No, you don't. It doesn't. I still have some old commands. Okay, sorry. Couldn't. Maybe this is non-linear one. Yeah, maybe this one works. Main code. Okay. Let's stop right here. Okay. Try this one. I just want to show you. Yeah, this one works. Nice. No, it doesn't. It stopped at some point. Also, due to version old version codes. This is 2018. Yeah, so this was the code where I generate those. Yeah, I was able to find the optimal point. Well, that's RBDO. That's let's Google what's the latest method. Yeah, it's been a while. Reliability-based design optimization. See this one. This one from 2000 1999. This is still the most popular one. Let's see what the latest. Data-driven RBDO. Okay. System RBDO. Okay. Effect time variant. They are still working on time variant RBDO. Basically, your distribution varies with time. And there's another kind is like a position variant. Like what I showed you earlier. Your distribution, you assume your standard deviation of your distribution is the. Oh yeah. You assume your so hold on. Am I? Can you hear me right now? Because I turned off my speaker. I guess. I guess I'm okay. I can turn off my iPad already. You did hear me, right? I hope. Yeah, no complaints. So I guess you still hear me. Okay. Anyway, uh, uh, earlier we assumed the standard deviation of your variable remains constant, like sigma equals to 2, and you said sigma is 2 everywhere. But what if there's a specific situation where your sigma varies with your position of your x? Then sigma is not constant. For that specific problem, it's a total different story. Let me see this one. Kriging method improve. I just wanna see if there's something new about this. If not, then whatever I did was already like the latest technology. I don't see new. Let me see. Novel method. A novel decouple time variant. Okay. Transform based improved kriging method for black box problem. Let's just read one paper. Okay, a bunch of 90% trust region, different training samples. Okay, this is like a MPP stuff. Dun. Okay, nice. Everyone is like trying to calculate the distance, right? This is in the standard normal space. This is where your constraint is. You're trying to find the distance. And what is MPP? Most probable point, the closest point to the to in the failure region. Okay, we call MPP. They solve crazy problems, crazy contours, and then use Greeking to approximate the constraints. See, the same problem. This is the exact same problem I show you. Everyone is solving the same problem again and again and again. Choi example, 1999. That paper. Since 1999, everyone just follow what they did. Ah, oh, I didn't. Haven't seen this problem before. So this guy show a bunch of RBDO problems. Okay, but method didn't change. Enhance. Did I just? I just showed that. I just saw that one. Layout optimization. Novel approach. Obstacle avoidance. Well, it seems like yeah, that's basically the latest technology. If you're interested, RBDO is like this. A lot of statistics, and the goal of developing a new method in RBDO is to avoid the usage of random generator and true evaluation of the probability. We call that Monte Carlo simulation. What's a Monte Carlo simulation? Monte Carlo simulation is like a randomly generate a bunch of points and then just truly evaluate all of them. Okay, so in our field, in RBDO, what I did by random generator basically was Monte Carlo simulation. Okay, so how do you know whether your design is good or not? At the end, you use Monte Carlo to evaluate how good it was. Okay, so the goal of developing RBDO methods is to avoid using Monte Carlo because it's too costly. Like earlier, when I tried to increase the accuracy of reliability analysis, I even tried to enlarge the number of sampling points from 1 million to more, and you can see how it did, what it did to my computer. It's almost crashed, right? So in real life, if you are truly doing reliability analysis, what do? It's very tough because in every step, like right here, there's a specific design. If your optimization method tells you to move to a new point, you need to know how good your new point is. You need to evaluate the function value. And when you do that, you basically need to calculate probability. And if you don't know any statistical tricks, you basically use Monte Carlo. So it's like whenever you make a new design, you make 1 million designs, 1 more million designs. So in real life, in your initial guess, you can do real life RBDO. Just make 1 million designs, and then count how many good ones, how many bad ones. So over here, sometimes you cannot converge in that case, because usually people use finite difference, right? So if your design point is right here, and you can see uh, uh, your your failure rate is 100. Ah, you will converge because the objective function will push you. So your objective function will try to push your design to somewhere, maybe here, and you start to see failure. That's where the feasibility gets in, and then start to push back your design point, move the point backward. Okay, and you optimization method finds the balance between optimality and feasibility. So, but whenever in every iteration, you are truly the bad way is to truly uh, randomly generate 1 million design. In real life, it's like if you are producing some 3D printing parts, you are doing a reliability based 3D printing optimization. That means right here, you need to make 1 million prints. Am I off? I'm still here, right? Oh, the call ends in 10 minutes. Okay, that's fine. I'm almost done. Okay. So in real life, let's say we try to do reliability based 3D printing optimization. Over here, you print 1 million parts. You evaluate how well they are. Then the optimization method tells you to go here. Then you make 1 million more at that particular design. And remember, for most gradient based optimization problems, you need to do finite difference. That means you need to have a final increment in x, finite increment in y. So you need to do this 3 times. If you need to do 3 times, that means you need 3 million of 3D prints to get the gradient. With gradient, then you can maybe move on to a better point right here, and then do it again. 3 million. Every move costs you 3 million prints. So in real life, it's impossible. However, when I show you RBDO methods, we based on statistical analysis, we were able to formulate equations that computes reliability without sampling. So these are the equations. Okay, and basically this RBDO is truly some material worthy research, graduate research, because since like 5 or 10 years ago, we were using the same method, and nowadays they are still using the same method. They just apply everywhere. Are you sure RBDO cannot improve? Maybe someone needs to work on this. So if any of you in the class are interested in this, come by and talk to me. Maybe I can show you more and work on this. So I had one PhD student. He's from India, and I think he graduated from Department of Mathematics. So when he came to me, I saw his CV. I thought he is really strong in math. I told him, hey, do you want to work on RBDO? He said yes. And then he started. We started to read some papers together. And one day he told me he wants to do experiments. That's how tough RBDO was for him. Okay, so at this point, I only have one in the past, in my 10 years of teaching career, only one student worked with me on RBDO. Yeah, his name is Su Ping. Yeah, he graduated. Anyway, my student would know who Shuping is. That's everything I want to introduce today, and we have no more lectures, no more. Next time we will see your final presentation. Let me remind you what you need to prepare for your final presentation. You need to give me a final document that could wait. On last week, if you need to add more on your final document, that's fine. I can give you maybe another week, but I will be traveling. But next week, I need your PowerPoint because you are presenting, right? So you need to focus on your PowerPoint first. And if you have any sample codes or anything that is related to this final project, at the end, zip them and then send to me. Okay, but next week I will listen to your final presentation, and then I need to speed up on my grading. Okay. Does anyone has questions? Okay, so I don't. I can see some of you, but I don't see anyone raise your hand or whatever. Um, this is just a sharing experience of my previous experience. I hope some of you would be interested in, or many of you may be just avoiding reliability in the future. To let you realize, okay, don't touch reliability. Anyway, but reliability is actually very important. Someone needs to work on statistics. Okay. Anyway, take care. See you next week. Bye bye. Bye bye.